Hey guys, this is the answer key to the nature of waves and also the sound worksheet, which is unit 6A and 6B. And these are the practice problems, not the note taking section. So you need to find those worksheets to go through them as I go over them with this video. So the first question says a child sitting at the end of the dock notices that 8 wavelengths pass by in 4 seconds. What is the frequency of the waves passing the dock? So frequency, the equation is that frequency equals the number of wavelengths divided by the total time that it takes for those wavelengths to travel. So he said that he had 8 wavelengths. So you see that the number 8, and then you have a little upside down looking y. That's called a lambda. And lambdas are the units for wavelengths. And then it passed in 4 seconds. So that would be your total time. So you're going to divide 8 by 4, and you're going to get 2 over 1, or 2, and you're going to have wavelength over seconds, and wavelength over seconds is a unit for frequency, which is called hertz, which is represented by a big H and a little z. So the answer to question number 1 is 2 hertz. Question number 2 says, what is the period of the waves from the previous question? And period is represented by a T. If you watch the video, you know that it was represented by a T. And so period equals 1 over the frequency. And so we have 1 over the frequency that we found in question 1, which is 2 hertz. So 1 divided by 2 is 0.5, and periods are measured in seconds. And so that is the unit. So it's 0.5 seconds is the answer to question number 2. So they gave you a diagram in question number 3, and it says to determine the wavelength and the amplitude. Well, wavelength is the point on one wave to the exact same point on another wave. And you can choose any point on a wave as long as you go to that same point on the opposite or the next wave. So they show you the lambda up there, and so they're showing you where the wavelength is. And so to calculate wavelength, you're going to go where it starts, which is at 1 on this particular example. And then it's the exact same point is at 5. So if you say 5 minus 1, you get 4, and it's measured in meters. So the wavelength for this particular example is 4 meters. If you look at amplitude, it's from the rest or equilibrium line, which is that middle line. It's all the way to the top of a crest or all the way to the bottom of a trough. And so if you look for this example, that wave goes all the way up to 2. And again, it's measured in meters, so the amplitude is 2 meters for this particular wave. Question number 4 has 2 parts. The first part says a pendulum oscillates 12 times in 4 seconds. So what is the frequency of the oscillations? So frequency equals, in this particular thing, the number of oscillations divided by the total time. So you have 12 oscillations and you have 4 seconds. So 4 divides into 12 3 times. So you have 3 hertz as your final answer for the frequency of that particular example. So for part B, it says, what is the period of the oscillations? You're again going to take your period equals 1 over frequency, 1 divided by the 3 hertz that we found in A, and that gives us 0.33 seconds for our period for this example. Now, the next couple of ones, we are probably not going to do any like this, but just so you know how it's done, and you can finish answering your worksheet and check the ones that you did if you actually did it, tried it. So in this one, it says, what is the length of the pendulum? So length is represented by an L, which this is a funny looking L, but it's above the G. So you have period equals 2 pi square root of length over G. And G is your acceleration due to gravity that we've already talked about a little bit. So we know that for our period, it was 0.33 seconds. And so we say 0.33 seconds equals 2 pi times the square root of L over 9.8 meters per second squared. So you do your math out, and you end up getting that the length is 0.027 meters. Again, you're going to use that same formula because you're doing a pendulum. This time the length is going to be given to you, and you're calculating your period So you're going to take, he says, what is the frequency is what you want to finally calculate, but you got to calculate your period first before you can find your frequency. So to find the period, you're going to say t equals 2 times pi times the square root of length over the acceleration due to gravity. So we've got period equals 2 pi times the square root of 0.25 divided by 9.8 meters per second squared. So you work that out and you get that your period is equal to 1 second. So to determine frequency from this point, you're going to say 1 over the period, which is equal to 1 over 1s, and that's going to give you a frequency of 1 hertz. For question number 6, you want to know how fast. You're going to want to know the speed of a wave. So it says a water wave has a frequency of 2 hertz, and there are 3 meters between each crest on the wave, so that would be your wavelength. And it says how fast is the wave moving. So we know that frequency is 2 hertz. We know that wavelength is 3 meters. So we're going to use our velocity equation, which is velocity equals wavelength times frequency. And speed would equal 3 meters times 2 hertz, which gives us 6 meters per second. And we will use the velocity equation in forces when we get to those. So 7 says sound waves travel at roughly 340 meters per second at room temperature. The minimum hearing range of a human is 20 hertz. What is the wavelength of the sound wave? So we've got our formula, speed equals wavelength times frequency. We know that the velocity or speed is 340 meters per second, and we are trying to find our wavelength, and we know our hertz is 20. So we set up our problem. We're going to divide 340 by 20, and we're going to get our wavelength is 17 meters. For question 8, it says if a spring requires 20 newtons to be compressed a distance of 10 centimeters, what is the spring constant? So we're solving for a constant here. And so we're solving for K because K represents our constant. So we have a force that is 20 newtons, and we're finding K, and our X is the distance that we're traveling. So in this case, we're changing that 10 centimeters to meters, which means we move it 2 places to the left, and we get 0.10. So we got 20 newtons divided by 0.10, and that's going to give us 200 newtons per meter for our answer. We're going to use this value in question 9. Question 9 says how much potential energy is stored in the spring from the previous question. And so our equation for potential energy is potential energy equals 1/2 the constant times the distance squared. So we've got our half times our 200, which we found to be our constant, which is newtons divided by meters. And our distance is 0.10 meters, and we're going to square that. When we do the math out, we're going to get 1. And the unit for potential energy is joules, which is capital J, and that is going to be the unit for energy for any problem that you have. All right, that was 6A practice problems. So now find your 6B practice problems, and we're going to look at this one. I'm going to make it just a little bit larger. So it says determine the wavelength of the longitudinal wave. Now remember, longitudinal waves come in compressed and then compressions and then rarefactions, and that makes up a wave. So on this particular example, you have 3 compressions and 3 rarefactions, so you've got 3 waves. So it says the wavelength of a longitudinal wave consists of 1 compression region plus 1 rarefaction region. And in the diagram above, there are 3 of each of these regions. Therefore, the wavelength is the total length divided by 3, which is 4 meters. So you got 12 meters there. Divide that by 3. 3 goes into 12 4 times, and that gives you 4 meters is your wavelength. Question 2 says a sound wave is determined to have a frequency of 1,000 hertz and a wavelength of 35 centimeters. What is the speed of this wave? So we have to change our centimeters to meters. So our decimal is at the end of that number, which is after the 5. We're moving it 2 places to the left, which gives us 0.35. And so in the problem, you'll see the wavelength already has it changed, so it's 0.35 meters. And then our frequency is 1,000 hertz. We multiply those together, and we get 350 meters per second. Question number 3 says if the sound wave in the previous question is measured in air, what is the temperature of the air? So we've got our 330 0.1, which is our speed of the sound wave. And then we got 0.6 and then our t. So we put in our 350 for our velocity of sound. Our 331 is for a sound wave in air is what our constant is. And then we got 0.6 and we got t. So we're finding t, which is our period in before, but this is going to be temperature this time. So then you do your math and you're going to get 31.7 degrees Celsius. And then question 4 is, what is the speed of sound in air with a temperature of 25 degrees Celsius? You're again going to use your constant equation there. Velocity sound equals 331 meters per second plus 0.6 meters per second times Celsius. And that is going to give times temperature. And so we're going to put in our numbers. We put 25 in for our T, which is our temperature. We do our math, and we're going to get the velocity or speed of sound is 346 meters per second at a temperature of 25 degrees Celsius. So question 5 says the hottest recorded temperature in the United States history is 134 degrees Fahrenheit, which is 57 degrees Celsius. What is the speed of sound at this temperature? Again, you got your two constant values that you're going to put in. Your only thing you're going to add is your 57, which is in the T spot. You're going to calculate that out, and at 57 degrees Celsius, our speed of sound is 365.2 meters per second. Question 6 says the human range of hearing is between 20 and 20,000 hertz. What is the corresponding range in wavelengths for sound in air at 25 degrees Celsius? So we have our 346, which we found to be the velocity at this particular degree Celsius in a previous problem. We have our wavelength, which we're solving for, and we've got our frequency, which is 20 hertz. So when we solve for wavelength, we get 17.3 meters. And we're going to use that to do some calculations at the bottom. So again, we put in our number values. We had 20 was our smallest hertz. Now we're doing 20,000. So we're doing that calculations and we get 0.017 meters. So the range would be from 0.017 meters to 17.3 meters, depending upon the amount of hertz that we had. So 7, the speed of sound in water is 1,500 meters per second. What is the wavelength of sound wave when a frequency of 15,000 hertz in water? So we got 1,500 meters per second as our velocity or speed. That's going to equal our wavelength, and we're timesing that by 15,000 hertz. And remember, this is in water. So our wavelength in water for these particular values is 0.10 meters. 8 says how much louder is a 70 decibel sound compared to a 50 decibel sound? So sound doubles when the decibel level increases by 10. So a 70 decibel sound is 4 times louder than a 50 decibel sound. Okay, so that's the answers to both practice problem worksheets 6A and 6B. Make sure that you know that the answers were derived. If not, come to a Google Meet and meet with me and we'll go over it. Google Meets are from 10 to 11 and 2 to 3 every day. So if you have questions, make sure you're popping in. See you guys later.